On the 6.3 quick check, we are using this equation, and this is one that is given on the AP exam. Now, this equation and this equation are just manipulated versions of this first equation. So you can see what's happened here. If we take the ln of KEQ and get it by itself, then we have to divide both sides by negative RT, so we get this equation. And then if we really want to solve for KEQ, then we need to take the E of both sides, so the KEQ equals E of this whole expression up here. Okay, things to watch out for. The value of R that we would use is 8.314 joules per mole Kelvin, and temperature has to be in Kelvin for this to work. And you're going to watch out because delta G usually comes in kilojoules, and this R we're using is in joules, so we have to take all that into account. So the first one here is, let's talk about this reaction. We've seen that a lot. Okay, water breaks up to be H plus and OH minus. And the delta G for that has been determined to be positive 79.9 kilojoules per mole at 25 degrees, or let's say 298 Kelvin, because we'll probably need that. So calculate the value of the KEQ. So using this equation, but really we're going to use this version of it. Okay, then we're going to say, well, the KEQ, in other words, the equilibrium constant, is going to be E to the negative. Okay, so delta G, so the delta G is positive 79.9 kilojoules per mole, okay, divided by the R times the T. R is 8.314 joules per mole Kelvin, okay, times T, which is 298 Kelvin. And because I have kilojoules on the top, I'm going to need to throw in that I have 1,000 joules for 1 kilojoule right here. So now my joules drop out, my kelvins drop out. Okay, so I have this number here. So I'm just going to do this number by itself first. So that's going to be negative of 79.9. Okay, my kilojoules are canceling out. That's okay. Okay, divided by 8.314 times 298 times 1 over 1,000. Okay, so that whole number comes out to be negative 32.2. Okay, we could say 249. It doesn't, that's going to be too many significant figures. Okay, so the value that I want is E to that power. So I'm going to try that. And on my phone, I'm getting that it is 1.0 times 10 to the negative 14. Okay, depending on where you round off these numbers, it's going to be somewhere around that. I've gotten 9.89 times 10 to the negative 15, but it's going to be close to that number. And that number should be recognizable as the KW, which is the KEQ for this expression. So we kind of know, yes, I'm doing the right thing. So that's how we do this kind of a calculation. Notice things we had to do. One, we have to use that value of R. Because that's joules, we have to change our joules to kilojoules. And we need to remember that this temperature has to be in Kelvin. So those things done, it's just a math problem. Okay, the second part says, well, consider a different reaction. Okay, carbon and water turning into CO and H2. And we have the delta H, delta S, and delta G. So what is the value of KEQ at 25 degrees? Well, we know the delta G, so we can do exactly the same kind of problem we just did before. So we'll do that in a moment. So I'll write it out and then you can see it. I took a moment and wrote everything out. Now I did it slightly different this time. It's an alternate way. And on the last time, what I did was I changed my joules here on the bottom into kilojoules. This time I'm going to change my kilojoules that's in my numerator to joules. So if I have 91 kilojoules divided by or multiplied by 1 joule per 1 kilojoule, so I'm going to have 91,000 as my numerator. And then the bottom here will be my R times my T, so 8.314 and 298 Kelvin. So I can see what's going to happen here. My kilojoules cancel out. My joules are going to cancel out. My kelvins cancel out. Okay, my moles cancel out. So I have E to the negative and I got 36.7295, and I've just put that in my calculator. I got this number, so I would report this as 1.1 times 10 to the negative 16, and that's my KEQ value for this. Now, that's a very, very small number, which means it's a pretty reactant favored, but that's not too surprising because my delta G is positive, which means, this is not a spontaneous reaction. We're actually going to end up with a lot more reactants than we get products. Now, the key question here is, okay, from this data, would you predict that the KEQ at 100 degrees versus 25 degrees, would it be higher, lower, or the same as you get at 25 degrees? Okay, so my KEQ, what I'm thinking, I would do it as a Le Chatelier's problem, and I have my equations. I have carbon, that's a solid, plus H2O, that's a gas. Okay, it's turning into CO, that's a gas, and H2, that's a gas. And my delta H is a positive number, so that means, the heat is going to be on the left side somehow. So if I increase the temperature, I have too much heat, that's going to shift this to the right, so that means these two values are going to get larger, this value gets smaller, that's a solid, it doesn't change its concentration. So if I did my KEQ, which is products over reactants, then I'm going to get a larger KEQ. So I would expect my answer to be higher, okay, a higher KEQ at 100 than I have at 25. I have heard some other people think, well, I could do a delta G equals delta H minus T delta S, and that makes some sense, okay, that if you had a higher T delta S, then that would make this a larger value, okay, and since it's minus T delta S, it would make it a little bit less positive, a little bit more toward the negative side, and so that means it would be a little more spontaneous, and we could expect that to be a higher KEQ, a little bit more product favored. I think the Le Chatelier's argument is a better argument as far as kind of clear, it makes more sense. Okay, so now we're going to test that idea, and we have our value here, KEQ at 100 degrees. Well, two things are going to change now. One is our delta G is going to be different, so delta G equals delta H minus T delta S. Since I have a different temperature now, I have 100 degrees, which would be 373 Kelvin, instead of at 25 degrees Kelvin, then that's going to change my delta G. And because I have a different temperature, when I put it back into that big equation, I'll get a different answer. So I'm going to take a moment and set this up. Okay, I've gone through and set this up, so I'm using delta G equals delta H minus T delta S. And from earlier in the problem, we saw that the delta H is positive 131 kilojoules per mole, and that the delta S is positive 134 joules per mole Kelvin. And my temperature changed into Kelvin is 373 Kelvin. So just do my math, and I have 131 kilojoules per mole minus, so I have Kelvin and Kelvin, and I have joules, 1,000 joules per kilojoule. So this whole expression over here comes out to be 49.982. So 131 minus 49.982 is positive 81.018 kilojoules, or kilojoules per mole. Okay, so that's my value of my delta G. Now I'm going to what I did before. I'm going to substitute in. So I'm going to do it like I did before. So my KEQ is e to the negative. So here's my 81.018 kilojoules. Change my kilojoules to joules. On the denominator, R times T. So joules. So joules and joules are going to cancel out. 8.314 joules per mole Kelvin times the temperature in Kelvin, 373 Kelvin. So when I do all that math together, I got negative 26.12538. E to the negative, I get 4.5 times 10 to the negative 12. Now I like to carry a lot of significant figures here because when I get to here, I get a lot of big variability, depending on where I round off. So I'm just going to try to not round off much at all. So 4.5 times 10 to minus 12. Now, the only thing that's important about that number is our prediction before was that our value would be higher. Okay, so this is 10 to the minus 16. Here I'm getting 10 to the minus 12. So that is higher. And so our prediction is correct, that the KEQ value would get larger at a higher temperature. And that's Quick Check 6.3.